turn off all these, then just that one is on, so you can decide what you want. It's Wednesday, so you have a 50-50 chance of people staying awake if you turn down the lights.
Yeah, right. Gotta balance it. Do I want them to be able to see or stay awake?
David, do you have any internet connections or any internet links on there? Okay.
Sorry, Frankie.
You have a place?
This is your place?
Huh?
Okay.
Hey. Hey, Jim.
Hey, yeah.
Long time no see you.
Yeah, it's been a while. We're all alive, still breathing.
Yeah. I was outside for 10 seconds. Just when we magic to us, we start.
Shall we turn the lights partly off?
Yeah, I think so. It's too hard to see otherwise. I think.
Jim, would you mind signing? Oh. It's nice to see you.
I'm not in the picture, am I? No, I got a good place on it. You tell me if I need to, you tell me? Yeah.
Nice to see you. Got the yin and yang of the physics department.
Great. The whole physics department here right now, don't we?
What you doing
it's
these
very-
days, Jim?
Teaching,
Teaching what?
English. 1302.
So that's writing.
Mhm.
What are they writing about?
Well, many things.
Are you teaching the film, writing about?
No, no.
Shoes and ships and sailing wax?
No, it's kind of like a mixture of things.
Okay.
This last 2 weeks, the theme was origins.
Okay.
So we looked at first 3 chapters of Genesis 1 week, to look at evolution the second week.
Have you seen the film The Life of Pi?
I saw that.
Isn't it
twice.
great? Yeah.
Wonderful.
I don't know how many times I've seen it. I keep watching it over and over again. on
I'm gonna watch it
HBO.
a third time.
Yeah, yeah. It's really masterful.
Did you see it in the theater, 3D?
Yeah, the first time.
Yeah.
Have any of you seen Life of Pi?
I haven't.
Did you like it?
I like it, but it's a film that you maybe have to see several times and think about that. Don't catch all the
That's true.
syllogism and philosophical part. And my daughter, that is a psychologist, she found more things that I don't find there.
I really liked it.
Yeah.
That was interesting.
What was the name?
The Life of Pi, P-I.
Okay. What was the subject?
Hard to say.
It's about a lot of things. It's about the power of narrative, the power of stories. But it's also about the existence of God, or the belief in the existence of God. It's very, very intriguing.
Have you heard of the Stanley Parable?
No.
It's a really interesting game that really focuses on narrative. It's really amusing too.
It's a electronic game, or?
Yeah, it's a computer game.
Oh. No, I'm not familiar with it.
It's very funny. It has a narrator and he tells you what to do, but you can choose not to do it and make your own narrative. It's really neat.
just wait another minute or so.
Oh, yeah, sure.
What's it called again, the Stanley?
Stanley Parable, I can show it to you on my laptop if you want to see it after the.
Okay, yeah.
It's a computer
Yeah.
game. But it doesn't have a lot of things that you would generally see in a game. There's no violence. You don't really interact with most things except.
No, I think that's great. I think that's the good way to
You
explain
have like
it.
a narrator that narrates your actions.
Sometimes I just think about what does this mean
Right, like
without any map.
one of the.
Yeah. Oh, it's true, yeah.
How would you explain it to somebody who didn't know?
Stanley chooses the doors to his left.
But yeah, this is perfect for the level.
Maybe.
Pitching with the narrative, and it's really fun.
Was it
I
in
like
my
a lot
area?
of
I'm not sure
photography,
grad school,
like
but
Alice, see that kind of.
directly behind it. So I had to study it out.
I think so.
Yeah, that's fine. I mean,
Stanley
yeah, there's
Parable.
something kind of cool and
Like,
interesting about it.
Yes, and run on.
Yeah.
So there's no
Project
further
stuff
to all this.
That's one of the
Right, as far as I can tell, we only have 3 of them.
Hi,
You teach it.
would you mind signing in for us?
Do you know where they might be here?
So you put it all the way through and-
Well, so far I've gotten 6 different endings. It's pretty short, but.
Yeah.
different
I did, I asked Betsy if she can find it, and do it tomorrow, so if she can't find it, we're just gonna do it for free, but if she can't,
Just like with Darling the Fourth is fast, right?
yeah, because I didn't realize that that was the result.
You know, yeah, we can get those fries up front.
I know, that's what
Oh,
I'm probably
yeah,
surprised.
really, I would definitely.
Well, that way downtown.
Yeah, I asked Betsy, she said she's gonna try to go to an She tried to get it.
Maybe it might be.
Auto store would have to.
She was like, that's like, yeah. She thought Radio Shack said they might have it like the audio store.
Yeah, we should.
She's gonna check it. If not, get more.
Yeah, it's gonna be much. Yeah, I forgot.
Yeah, I'm kind of weird my own way because I work a lot of
Yeah.
so mean to Greece.
Yeah, no, I understand.
Yeah, I mean, I wrote it my own way, kind of totally different based on what I wanted them to see. I got to do that tomorrow.
I might have on hand.
Yeah, we did the LRC lab, so they will.
All right.
I own the right section. I am. Oh, I love it.
And all that's only going to start with.
I can scan it.
My assignment is going to stay seated. All right, why don't we get started? Did everyone sign in? We'd appreciate if you would please do that. If you just have the way out, if you would. It's a great pleasure to welcome David Stancato today from the physics department. Thank you very much for putting this together for us. And David's title is The Dark Side of the Universe, Dark Energy and Dark Matter.
All right, so let me turn that. Yeah, that way everyone can see it. Make it dark. Yeah, it's gonna be dark, the screen's gonna be dark, everything is dark. So Ron asked me to talk about something in the physics world which is current and interesting, and I thought a lot of people like to know about this subject, dark matter and dark energy. I assume many of you have heard the terms before, maybe on like some show or Discovery or one of those types of things. So I want to talk a little bit more about what it is. Obviously, I'm going to keep it at a level that hopefully everyone can understand and grasp. No heavy mathematics or anything like that. So let me get started. So what dark? I mean the word dark. So the dictionary definition: with little or no light, not reflecting much light, approaching black in shade. So kind of think about that and what it actually has to do with the two quantities I'm going to talk about, dark matter and dark energy. So one of the questions that I think people have, or people that have not delved into the subject, is, are these things the same thing? Okay. Are they related to each other? Why is one called dark matter and the other called dark energy? So are they related? Are they the same? The answer is no, not even close. Okay, they're not even related to each other at all. They're totally separate things. They just have a name that sounds similar. So I'm going to talk to you about each one in turn. I'm going to start with dark matter, and then I'll talk about dark energy. They're really very different things. The word dark, as we'll see, kind of symbolizes a couple of things about this subject. All right, so it's called dark because there are two quantities. One is a form of matter, as far as we know, and the other is dark energy is something we don't really understand very well, so it's kind of hard to even call it, to know what to call it, but we can't see them, okay? Usually when we try to detect something, we need to be able to see it, okay? And I don't necessarily mean with our eyes, although I detect, I look at Ron and I detect him because he has light bouncing off of him and hitting me in the eye, so I say I detect Ron's presence. We can detect things without our eyes, with instrumentation, but generally we're still looking for photons or particles of light to hit something and then cause a reaction in our instrumentation. Our instrumentation says, here it is. All right. These two things, they don't seem to emit, reflect, absorb light at all. So they can't be seen. All right. The other meaning of the word dark is that because we're so ignorant about it, it is dark. We have no ability to see literally and figuratively what these things are. So, of course, the question is, what do we know about them? All right, and I'm going to start with dark matter. So dark matter is, by definition, in some sense, a type of matter which exhibits gravitational effects, meaning it pulls on other matter, causes it to attract. All right, but it's a kind of matter that doesn't seem to absorb, reflect, emit enough light, at least not enough light for us to be able to detect. Okay. So we are matter which reflects light quite well. The sun is a form of matter which emits light very well. This type of matter does not emit or reflect or absorb light. It doesn't do any of that. Okay. So that's what we're going to focus on first, this idea of dark matter. Questions we might ask are, how do we know it's there if we can't see it? Okay. And why do we care if it's there? All right. So I'm going to talk about those two things. Okay, so we can't see it, all right? We're like this guy, llama, kind of cool hair. All right. All right, so what are some evidence for this existence of this stuff that we can't see, all right? There's actually many lines of evidence. I'm going to talk about two of them, okay? The first one I'm going to talk about is stars and galactic rotation. And the other one I'm going to talk about is gravitational lensing. And I talk about these two because in some sense they were some of the major pieces of evidence for the existence of this stuff. And secondly, because they're kind of interesting in their own right, apart from whether there's dark matter or not. So let's talk about stars and galactic rotations. Here we go. So the basic idea is as follows, with this kind of experimentation, this kind of evidence for dark matter, is you look at a galaxy, and you look at all the stars in that galaxy, and astronomers are very good at counting stars and counting the amount of light that comes from a galaxy. And we generally know about how much mass each star would have given the amount of light that it outputs. Okay? That way we can look at a galaxy and estimate reasonably accurately how much mass that galaxy has, just based on how much light is coming to us from that galaxy. Okay, that's step one. Step two we know that the galaxy's mass causes stars to rotate around. In other words, it's very similar to us and the sun. Okay? The sun causes us to rotate around. If the sun wasn't there, we would just fly off. All right? But the sun causes us to rotate around, and in fact, by the speed at which we rotate around the sun and the distance we are from the sun, we can actually infer exactly how much mass the sun has. Then we also look at the sun and we say it's a star of this brightness, so we can tell how much mass it has that way, and both ways give us the same amount of mass. So that's basically the idea. We look at the stars in the galaxy, we say, I can count the stars, count the amount of mass, then I watch some stars rotate around the galaxy, okay, and I measure their speeds that they rotate around the galaxy, and I measure the distance that they are from the center of the galaxy. That'll tell me how much mass is contained in the galaxy. If there was too little mass, the stars would all fly off. If there was too much mass, the stars would be pulled in to the center. So there's some intermediate range, that the actual mass of the galaxy, such that the stars rotate in the way that we actually observe. Okay, so that's the basic idea. Take two measures of the mass. One, based on the rotation of the stars, and the second measure is based on how much light we can see from the galaxy. Okay, are there any questions about that? Yes. Feel free to ask questions about it. Yeah.
What determines the mass?
The mass of, well, how much mass is there? That's what it would be, all the stars. Or what we would have thought was all the stars. We would have assumed that the mass of the galaxy is totally determined by all of the stars in the galaxy. And what we're going to see is that's not true.
What pulls those stars in? That mass?
The stars themselves pull themselves in. That's right, originally. And now,
The whole sun, like we have.
there's probably a black hole at the center of the galaxy, which is very important in keeping the galaxy together, but that would be another portion of mass in the center of the galaxy. So we'll talk a little bit about black holes in a second, about what they have to do with this story. Yeah, Dan?
Is there something that automatically precludes us from concluding that this mass might not just be non-luminous matter, just dust that is just perfuses the area of the galaxy?
Yeah.
Is there a way to exclude that possibility right away?
Right, so we'll talk about that in a little bit. But no, that's good, that's good. So Danny's saying, well, couldn't it just be stuff that we can't see, but not anything special, just like lots of dust floating around or something, kind of hydrogen, helium atoms floating around, and that would seem to be a possibility. But right now we're just comparing the luminous mass, the mass we can see, to the mass that we kind of infer based on how the stars rotate. Any other questions? Okay, so let me show you a graph of what the experiments show. So this graph is not meant to be too confusing. This x-axis is the distance from the center of the galaxy. So you look at a star out there somewhere. You measure its distance from the center of the galaxy, and you plot on the y-axis the speed of rotation of the star as it goes around the galaxy. And you see what the calculated graph should look like. In other words, given that the mass that we see, the luminous mass, the stars, as they get farther from the center, should be going faster until they get to about this point. And when you get way out from the center of the galaxy, the stars should be traveling, actually rotating slower, okay, than they were at this kind of special point right here. Okay, so the stars, when you get real far out, the stars should not be rotating that fast. That's based on if all the mass that was there was stuff we could see. Okay? And this is what they actually measure. Okay? So all the way even out here, this far from the galaxy, the stars are still moving quite rapidly. Okay? The only kind of conclusion that you can get from that is that there's more mass there to keep these distant stars rotating rapidly. That though there was not as much mass in the galaxy, the stars would rotate less and less rapidly the farther they were out from the center of the galaxy. So there's obviously some physics that goes into calculating this graph. It has to do with Newton's law of gravitation. Okay, but that is assuming that's correct. This is what the stars should do. This is what the stars actually do in terms of their speeds of rotations. Okay, so really quickly, the first person. Sorry. So the first person to discover this was actually back in 1933. All right, so everyone chose this picture because it's funny, because he was kind of a funny guy, it seems like, kind kind of cantankerous. And he discovered a lot of things in astrophysics. He discovered this effect that there seems to be a disconnect between the amount of mass that we can see and the amount of mass that we infer from the rotation of stars. Of course, in 1933, the experimental abilities and observational technology was not so great, so no one really believed him back then. He also discovered the idea of things called neutron stars and other things, so he was actually quite a pioneer, way ahead of his time. Much later, in 1970, astronomers team led by Vera Rubin was able to demonstrate this effect with better equipment, so to speak, and people started to believe it. Okay, that there was this huge disconnect between the amount of matter that we can see and the amount of matter that we have to infer based on how the stars are rotating. Okay, so the conclusion that comes from this is all galaxies contain much more matter than we can see. All right, and that, unless Newton's law of gravitation is wrong, which some people have thought about, okay, then this is true. Okay, all galaxies contain much more matter than we can see. So that is the only line of evidence. So I want to go over one more other of the many lines of evidence that that astronomers and astrophysicists and cosmologists have been able to come up with. Okay. Clicking it once, it's going twice. All right. So the other line of evidence is called gravitational lensing. Gravitational lensing is really cool. In 1915, Einstein discovered that mass and energy bend space and time. It's kind of hard to imagine what that means if you don't study it enough, and even if you do study it enough, it's still hard to imagine what it means. Okay. So the point I want to get across in this talk is what that means is light follows. We know that light travels in straight lines. If I shine a laser pointer, it seems to hit the board fairly straight in front of me. However, if space itself is bent, then when light's traveling straight, it's really curving because the space itself is bent and light's just following this path in space, which is curved. Okay, so you can see kind of a basic idea here is the presence of mass anywhere bends light. Okay, even the Earth bends light. It turns out the Earth is a very small amount of mass in a relative scale, such that it doesn't bend light very much, right? But it does bend light. So here's a basic picture. It's kind of an interesting picture. So this effect has been observed. We have a star which is located somewhere behind the sun, and its light is traveling, and it's traveling straight, and if the sun wasn't there, the light would just kind of go off like that, and we would never see it, because it would never hit the Earth. But in reality, the sun bends space around it, causes the light to seemingly, from our perspective, curve, and this light ends up hitting the Earth. And so we look at this light and we assume it traveled in a straight line, and so we think the star is actually there, but it's not actually there. The star is actually here. Okay? This is very similar to what? What effect? Refraction, that's right, with anybody who wears glasses or contacts. This is happening to you all the time. In fact, the glasses are making something appear to be somewhere where it actually is not. So your glasses are, in fact, fooling you. Okay, into thinking the object is somewhere that it's actually not. All right, we're being fooled by the sun into thinking the star was here, whereas in fact it was right here. Okay, so this is a cool effect in its own right. It's called gravitational lensing because unlike a lens made out of glass or plastic, it's a lens in space itself. Okay, caused by the mass of the sun. Okay, now there are other masses which are much bigger than the sun. For instance, galaxies and so forth. Okay, so we can see this effect not just with stars, but with larger bodies. Okay, so here's a really cool picture. So you look at this, you might not know what it is at first. Okay, so this thing right here, this big bright thing, is a large galaxy cluster, a galaxy LRG 3757. Okay, someone named it that. All right. The interesting thing is not the name of this galaxy; it's this kind of a ring-like thing here. It's kind of, what is that ring? What? Okay, no?
It's something behind it.
It's something behind the star, but it's one object. It's a point behind the star. It's the light is coming to us from behind the star, coming towards us, but this object is so massive, as the light diverges out, it curves it back around and comes to us like this. So where does the light appear to be coming from? Out here, up here, down here. So this is a totally distorted object, which is point behind this giant galaxy. Okay? We see something that there's nothing here, there's nothing here, there's nothing here. Nothing actually exists there. It exists behind this giant galaxy. And we get to see it in this smeared out it's like a very, very powerful lens, okay, that distorts this light dramatically. This is almost a complete ring. Such an object, it has to be has to line up just perfectly to make a perfect ring like this. It's called an Einstein ring. Einstein was the one who first predicted that this could happen. He never saw it because observations weren't good enough, but he predicted that it could occur. So let's look at a couple more lenses. So this kind of central region is a bunch of massive galaxies, all right? And it's kind of hard to see, but you can kind of see some smeared out little scratches here, okay? And those are not smeared lines, those are single points which have been completely distorted by these masses which are bending space-time, causing this light to completely distort, okay? This is an object, and these four things are exactly one object behind behind this object that comes to us and appears to be four objects. But they don't actually, these are not different objects, they are the same object. Okay, the light has been distorted. All right, any questions?
Does that mean that the object behind that is close to the one in the middle?
No, it can be very far away. Yeah, it can be very far away. Yeah, Mike?
So David, the Einstein circle makes sense to me. Because
Yes.
if there's an object back there, it would tend to make a ring.
Symmetric, yeah.
The cross, though.
Yeah, so the cross is, I'm not exactly sure what distribution of mass creates the cross. It's not as clear. This object is not a point,
Okay.
and these objects behind it, there's not points. So usually you don't get this perfect Einstein ring. It has to be technically a point of mass in front of another point of mass directly in front of it from our perspective, and then you get that perfect Einstein ring. Most of the study of lensing are things like this. Even this is considered a dramatic example. Most examples you couldn't really even see just by looking at it. You have to really go through the data and say, okay, there's lensing happening in this frame, so to speak. Okay. So what's the point as it relates to dark matter? Well, we have another way now to measure the mass of something. Because the amount of mass, if I go back to this picture, this mass here, however much mass that has, is going to determine how much this light gets distorted from this thing in the back. Okay? So what's the basic idea? Observe the bending of light by some galaxy. Okay? By how much that light is bent, we can infer how much mass that galaxy must have. Because given an amount of mass, that tells us how the space will be bent. Okay? Then we also just look at that galaxy and look at how much luminous mass it has, how much light it outputs, and how much mass that light should correspond to, and compare the two. So there's a whole extremely active area of research in taking these pictures that you see, these basic pictures, and calculating what mass there is to cause these distortions of these stars and galaxies that are behind them. Okay? So that's this is actually a picture of, not only do they know how much mass is located in the galaxy that bends space, but the distribution of mass, where that mass is located within that galaxy. They can tell all kinds of things about the mass of a galaxy based on its ability to bend space. It'd be very similar to taking a lens, holding it in the sun, and you know a lens will focus the light rays, and by seeing how far the light rays focus, you can determine all kinds of properties about the shape of the lens and how it bends that light. Well, that's what they're doing, except they're determining all kinds of properties about the mass of the object that is bending this space. Questions? Okay, so what's the conclusion? Clusters of galaxies contain much more matter than we can possibly see. Okay, same conclusion, just a totally different line of evidence. All right? And there are many other lines of evidence as well. So we believe that there is more mass there than we can see. All right, the question is, of course, what is it? So Danny, how hypothesis, all right, that it's some kind of dust. Okay, we'll take a look at that in a second. When they look at all of these lines of evidence together, they get a picture, which is kind of startling, which is that the mass of dark matter, the stuff we can't see, appears to be approximately 5 times as great as the mass we can see. Okay? So it's not like there's stars and then a few percent extra stuff. 85% of what's out there, of what mass exists in the universe, is mass that we cannot see. It's undetectable mass. Only 15% of the mass is something that we can detect. Things like stars and, well, mostly stars. Okay, stars and clusters of stars. Okay. So most of the universe is dark. All right, so historically there have been 2 explanations for this. The first explanation historically, well, this isn't actually in the order historically, but the explanation I'm going to go through first is the explanation called MACHOS. Okay? MACHO stands for Massive Compact Halo Object. The second explanation is the explanation so-called WIMPs. Okay? So these were obviously, one was named and the other was named in making fun of it. Okay? So let's talk about MACHOs first. Well, massive, okay? Massive means it has some mass, okay? Compact means it's small. The small means small relative to the whole size of a galaxy. And halo, that has to do with where it is located in the galaxy. Okay. So MACHOs, the basic idea of MACHOs is people said, look, there's some stuff out there we can't see. In fact, 85% of what's out there we can't see. What is it? Okay. So one camp, or one hypothesis, is that it's just normal matter. By normal, I mean protons, electrons, neutrons, all the things you learn about in school that make up atoms and molecules. It's just that those types of matter form kind of possibly unusual objects like black holes, neutron stars, brown dwarfs, which are kind of stars that aren't big enough to light up, okay? Just kind of dead stars, and planets, and then even dust, as Danny said, would be included on this list as well. Stuff that just doesn't light up, so we couldn't possibly see it. Okay? So people have looked for these things, and they've studied how much of these types of objects should exist in the universe, and then observed them. And I'm not going to go through all of the arguments, but what almost all physicists conclude is such objects exist, and they do not make up even close to the amount of matter necessary to reproduce how much matter we detect or we infer. Okay, so these appear to be not correct. Okay, or at least they exist, but not enough to really give us our missing matter. Yeah, Dan?
Is that coming from Big Bang Theory? What should be?
Not the show. I'm sorry? Part of it.
Part of it.
Mm-hmm. That's right. So it doesn't match up with the abundances of elements that should exist and things like that. So there are lots of lines of evidence, not just that, but also these things wouldn't be distributed in a way that is seemingly very consistent as well. So there's a couple reasons. Okay, so we got to go to the second category, which are called WIMPs. Okay, a very different type of idea. The basic idea of a WIMP is that there is a new fundamental entity in the universe that we don't understand. A fundamental elementary type of particle, like we have electrons, we have protons, we have neutrons. There are even other weird types like muons and neutrinos and things that we actually, even though not everyone necessarily knows about them, physicists know about them and we understand them quite well. Okay? All of those things would reflect light or emit light, okay? Except for neutrinos, but neutrinos aren't a good candidate either. So it must be some new type of particle that we don't know about. Just don't understand what it is. Okay? The new particle does not interact with electric charges, and therefore it can't emit, reflect, absorb light, all the things we said. The new particle only interacts with other objects via something called the weak force, which is, as it sounds, a very weak force, and hence the name weakly interacting. Okay, weakly interacting massive, because it has to have some mass to it to create all this mass out there, particle. So where would this particle be? Well, it's a fundamental particle. It's tiny. It's subatomic. So it would be everywhere. Okay, they'd be in this room right now. They'd be everywhere. We can't see it. It goes right through our bodies. Nothing ever happens. Okay, because it doesn't interact with the types of materials that make up our bodies. So they'll be thousands, millions, however many you want, in a given region of space. Okay, they would exist everywhere. We just wouldn't be able to detect them. Now, that's a great idea, but not very useful if we can't detect it. So we are still going to try to detect these things. Okay, how would we do that? All right. A couple ways to try to detect these objects. There are actually three basic methods to try to figure out what this dark matter, so-called WIMP, is. Okay, what type of thing is it? All right, the first way is direct detection. If indeed it is a weakly interacting massive particle, they would every so often hit something and cause a collision. And by these I mean subatomic collisions. Okay? Every once in a great while. It wouldn't happen very often, but every once in a great while. So you build a detector, okay? You hope one hits in your detector and it produces perceivable, detectable things, okay, when it hits. Things that we're used to detecting, like electrons and photons. Okay. The second way is that if all these things are existing in space, these WIMPs would be out there, and they might collide with one another, and it turns out when things collide with one another, they can sometimes destroy each other. Okay? In the process of destroying each other, they produce other particles that we understand, and we can detect those things. So that would be another hope. Okay? And the third would be, we hope to be able to make them ourselves. Okay? And the way we would make them ourselves is by smashing two protons together, and that makes a whole mess of subatomic particles, and we hope that one of them would be the WIMP. Okay? So those are three different ways we hope to detect WIMPs. Yes?
Are there any current particle physics theories that predict a WIMP that would predict the properties that people are looking for?
Many, many.
Okay.
Okay, so there are many theories in particle physics. Particle physicists are interested in formulating theories about the particles which make up nature. We have a really good theory that describes all the particles we know. That theory is actually relatively incomplete, or there could be more particles, and there are many theories which predict more particles beyond the ones we know, and some of those would be perfect to be a WIMP. In other words, it would have the right properties as a particle to be this particular particle. This is why this idea has so much traction, is because not only is it just a guess, but there are many, many theories which seem to make a lot of sense, although they haven't been experimentally verified, that predict that such a thing would indeed exist and should exist in the universe. Okay, so these are the three ways we're hoping to look for them, and if we can find them in any one of these three ways, it would tell us that one, it exists, and two, it would give us some knowledge of what type of WIMP it is. Okay, so how do we do these things? Well, here, unfortunately, you have a few problems. How often are these hits going to happen? Not very often, because this dark matter is so weak in its interactions, it rarely ever interacts. So if we have a detector here on this table, that's a bad choice, because there's light in this room, it's hitting the thing. We can't possibly kind of stamp out all the noise from all the normal things hitting this detector. So we need to go deep underground where we can block all the normal particles, the photons and the electrons and the protons, from smashing into our detector. So we have to go underground. Here we see one of the mines that they go under. I had a friend in grad school who went to live in a mine for 6 months to do this work. Yeah, 6 months. Yep. I'm sure they got to go out every so often, but they were. That's where their research was, in South Dakota in a mine. Okay. You go down there, you put a detector in there. Here are a couple in North America. There are a couple other ones in Europe. Use an old mine site, basically, and go down there and build a detector. Something which you hope the dark matter will every once in a while hit, and you can detect what happened when it hit. Okay. Difficult to detect, like I said, must go underground. Seemingly no strong evidence for such a detection. There are always, as you can probably imagine, a very delicate experiment would be needed, and so there are always many experimental difficulties with making such an experiment, and no evidence that people are kind of uniformly behind yet on whether anybody's seen anything doing this. Okay, the other type is indirect detection, where you hope that two particles have collided in space, these two WIMPs, they produce some other particles, we detect those, and we can then deduce the properties of the things that collided in the first place. We have to go in space to do this, because the atmosphere would totally ruin any particles coming towards us. It would be unable to detect them properly. So we have to put a detector in space. It's difficult to know if one of the particles we detect comes from a dark matter collision or just from, you know, some star blowing up somewhere. Okay? So obviously astronomers have to be astrophysicists have to be very key in this, because they have to tell us, you know, how many stars do you expect to blow up? How many weird processes do you expect to spit out particles? Okay, and we have to see if there's something more than that. All right, they just put one of these on the International Space Station. It just had results in spring. The results show an anomalously large number of protons in space. Okay, positrons, excuse me. Positrons are a type of fundamental particle, kind of like an electron cousin. And that seems to be a strange amount of positrons that they detected. One hypothesis is that these positrons are coming from dark matter that's colliding. Okay? And another is that there are strange astronomical objects that shoot off lots of positrons. From what I've read, and I was looking into this recently, the range of kind of excitement about this is, oh my God, we detected dark matter, to we don't know anything more than we did before this experiment, because we can't say anything about where these are coming from. Okay. Well, the most cynical person I saw said, we have a really good new data. It just doesn't really necessarily tell us anything yet. Okay. So because the data is good, but we don't know where these positrons are coming from necessarily. They could be coming from normal processes. Yeah.
Is positron, is that antimatter?
It's an anti-electron.
And where did antimatter fit into the possibility that antimatter in the universe is
well,
dark?
Antimatter would also interact with light, because it's just like an electron,
Right.
but the opposite charge. So it would interact with light in almost exactly the same way. All right. So what about producing these things, actually creating them ourselves? Okay, the way to do that is to smash particles together. And as Mike asked, he said particle physicists have a lot of ideas that in fact these dark matter objects should exist, and they should exist if we smash something together, they should come out. Okay? Some theories predict this, some theories do not. The Large Hadron Collider at CERN, Atom Smasher, is hoping to test this possibility. For some of you may know that it discovered the Higgs boson, which is a different talk in and of itself. That was one of the reasons it was built. One of the other reasons it was built was to try to produce dark matter, okay, in the detector itself. Now, it's hard to detect, so it would leave the detector. We would never see it, but we would infer its presence because there would be something missing from what we detected. Okay? And that actually tells us a lot, surprisingly. So it seems that there's no dark matter at the LHC yet. Doesn't mean we haven't created any, just means we haven't been able to kind of infer its existence yet, or the LHC also has not reached its maximum capability yet, because it's been kind of ramping up in its power. So in the next few years, we should get some better thoughts as to whether this is actually producing any dark matter. Any questions?
Well, what's the difference between dark matter and antimatter?
Okay, so antimatter is it was discovered in the 30s, actually, that every type of particle that exists in nature has what we call an antiparticle. Okay? So an electron has an anti-electron, which gets named positron. Okay? A proton has an antiproton, and so on and so forth. An antiparticle is the same as the normal particle, that's its cousin, so to speak, except that it is an opposite electric charge. So an electron has a charge of -1, so a positron has a charge of +1. A proton has a charge of +1, so an antiproton would have a charge of -1. And we discovered, theoretically, actually, it's an amazing story, theoretically someone predicted for every particle there must be an antiparticle in existence. And then we discovered it a couple years later that there are such things. So antiparticles are similar to the normal particles, except everything's the same about them, except the opposite sign or type of electric charge. Dark matter is a new particle completely, doesn't fit in with anything that we know yet, has no electric charge, and is more massive probably than most of the other particles we know. So there's no relation, even though they both sound kind of scary, I guess. It's the antimatter, dark matter. Yeah.
So David, if we manage to create dark matter particle, we're going to be creating anti-dark matter
Yes, yes.
And if we create so many of them, since we can't see them or detect them, we don't know how many we've created. Are we gonna create so many that we're gonna throw the weight of the mass or something off?
No, no. So these things are very small in mass. There would just be very, very many of them.
It's hard to imagine.
It is hard to imagine. You have to realize that these particles, when I say that this particle, this dark matter WIMP is massive, by massive I mean maybe 10 to the minus 24th kilograms, as opposed to 10 to the minus 27th kilograms, which is the mass of a proton, for instance. Okay, so I'm not talking about large things on our scale, I'm talking about large things on the atomic scale. Okay? And there would be so many of these particles that they would make up all of this dark matter, this 85%. Yeah?
Why is the effect only detectable on massive objects? Like how come you can't show things on a hat, for example, influencing any strange effect like that? Why is it only massive particles in space, massive object in space, where you can actually see that?
Well, part of the reason is because the force of gravity is actually very weak. So if we take your hat, for example, it's attracting that cup. It is. But it's a very weak attraction because neither the cup nor the hat have a lot of mass. So we need extraordinarily large masses to have a strong enough force to detect these effects. And only in space do we have bodies that have large enough masses for this to happen. That's part of the answer. All right, any other questions? Okay. All right, so why is this important besides it be kind of interesting to figure out what 85% of the mass in the universe is? People want to, physicists like to know things, what exists, okay? Two reasons beyond that. The first reason is the actual amount of mass in the universe influences how the universe itself evolves. Okay, so as I'll tell you later, the universe is expanding. And the amount of mass in the universe tells us how the expansion of the universe will either continue or not continue. Okay, so knowing how much mass there is very important for understanding actually everything about the universe, okay, in terms of its kind of evolution as a whole. And number two, if dark matter is indeed a kind of a WIMP, then knowledge of the properties of that WIMP would help particle physicists to understand the underlying laws and basic constituents that make up the universe itself. Okay, so this is quite a key to understanding quite a few things in physics from on a fundamental level. So dark matter is important in that sense. Any questions before we move on to dark energy? Yeah.
Maybe this is a crazy question, but so the massive object in space, why not, instead of saying that the WIMPs are everywhere, why can't you say that the massive object has a relationship with the space near it? It changes the composition of that space so that the appearance of the mass is apparent.
So it changes the composition of space.
Right.
And changes what's there,
well,
or changes...
Like a planet deforms space.
It does, that's right.
Why could it also change the composition of space, make it more massive?
So like put more objects there with it, or just... Because mass is a property of matter. So it's a property of some object. So there are theories that maybe we're just measuring these things wrong, not because we're bad at measuring things, but because Newton's laws themselves is wrong. Okay? And if Newton's laws are wrong, technically general relativity, Einstein's theory of gravity is wrong, then it would throw off all of our calculations as to what should be there. And then that would lead to this effect. But we feel that general relativity is probably correct as so far as it says about this subject. So yeah, I mean certainly mass does cause space to change in its appearance, so to speak, in its shape. But even if it did somehow change the composition, then that would be interesting in its own right, and we want to figure out how that composition changed, and it would be something that it changed. So we'd be looking for that as well. Yeah, Mike?
When I think of mass of an object, I think of basically the sum total of its protons and neutrons and electrons. So dark matter, from what you're saying, it sounds like it's not connected like those are.
Right.
So it's not necessarily because I step on the scale and I weigh as much as I weigh, as I say that. But that number doesn't determine how much dark matter is associated with me.
Well, it would actually, because the dark matter would have the same gravitate. You're measuring a gravitational effect when you step on the scale. We just assume that that's the number of protons, related to the number of protons, neutrons, and electrons in your body. Now, your body would probably not have a lot of dark matter bound in it. It might have dark matter running through it, okay, but it wouldn't have dark matter bound in it, because dark matter wouldn't form kind of bound particles because it interacts so weakly. But anytime you're measuring a gravitational effect, you're measuring all of the mass, and in fact all of the energy in that region, not just the protons, electrons, and neutrons. Yeah.
Your diagram there had a with the sun and an indentation there, I guess.
Yeah,
bending
that's
space.
right.
Now, if I were to put something on a cloth, right, and drop it down, it would shrink.
Okay.
I mean, it would drop down. Is there a consistency to the space fabric where you actually have additional fabric there to allow for the bodies there? I mean,
In some sense, yeah. In some sense, the mass would not only bend space, it would in some sense create or remove
kind of
space.
duplicated. Maybe that's what they're looking at. It was the fact that there's extra added because of the bodies that are there that are creating the. I mean, there has to be a consistency there, so you have to add more fabric.
But it would add more space, but it would. But we already taken that into account in the analysis of the light.
I hate to ask questions like this, but it bothers me that we don't have a superconducting super collider. Is there any thoughts that maybe CERN isn't up to the task of creating dark matter with the superconducting super collider would have been, with the energies it could have produced?
I don't know. It would have been more energy. Most of the interesting stuff is expected to happen at the LHC's energy. But then the more it doesn't happen, the more people think of ways it could happen at just a higher energy. So yeah, it's kind of hard to say. So if those of you who don't know, there was going to be a very large super colliding device built in Texas. Would have been the world's best. Okay, would have been better than this, and it would have happened, almost 20 years ago now. It was supposed to be built, but it got canceled by funding, Congress, and all that stuff. So okay, it's partially built. The tunnels are there. Where are they? Do you know where they exactly are? Where is that? I gotta go.
By town now.
Okay, yeah. The tunnels are still there. They're empty, I guess. They're just.
No, it's being used.
Are they?
Yeah.
For what?
The military group is using that to train people. Is a private company training people there for doomsday.
Really?
Yeah.
Oh, interesting. All right.
I have a question.
Yeah.
What is the definition of space? I'm sorry.
Okay.
Yeah.
What is the definition of space?
Is it?
Difficult
It looks like an indentation. What is?
Difficult question. There's not really a good way to define space. There's a good way to define, say, a distance in space. Okay. There's a good way to define an amount of time that has passed, but to define space and time itself is actually an interesting question.
Set of laws, maybe.
more
Set of laws.
The
Is it like a set?
Not
like a set of
necessarily.
principles?
Physicists try to define maybe space and time are not actually kind of properties that we should just take for granted, but maybe they actually come from something.
Properties.
That's another talk that I'm not even that qualified to give. But
It's just a list. It's a set of properties. It's just a set of.
in a certain
laws.
sense, this is the way we see it. It's a geometry on which we interact.
They say that space was created at the Big Bang, space itself.
Space is continually being created even today. Yeah.
Expansion.
Right. So it's not as passive as it seems. Shall we move on? Okay. So now I want to talk about dark energy, which, like I said, is a totally different subject. But first, I want to talk a little bit about the expansion of the universe. So in 1929, Edwin Hubble showed that the universe is expanding. Okay. So in other words, on average, everything in the universe is moving away from everything else. All right, on average, on a big scale, obviously, and everything's moving away from everything else. But if you look out there at the galaxies, they're all pretty much moving away from us. Okay, And if you were in another galaxy, you'd see all those galaxies, you'd see all the galaxies that you could see from there moving away from it. Okay, so everything's moving away from everything else. Talking a little bit about how he showed that. It's one of the major early pieces of evidence for the Big Bang as a theory of the universe. There are many, many other pieces of evidence, but I won't go into those. So it's kind of a long time ago, 1929. Created a bit of a shock wave, as you might imagine. Whoa. So I want to talk a little about how he did it, and it'll allow us to understand a little better about what I want to talk about in regards to dark energy. I want to talk about something called the redshift effect, or it could also be called the blue shift effect, but we tend to call it redshift. If you have a wave which is created by something, so imagine, for instance, a sound wave created by a speaker. You might have all kind of experienced this, that when the wave source is moving away from you, it changes how the wave sounds. So if you're standing there on the street and an ambulance goes by, and as the ambulance is moving away from you, the ambulance somehow sounds different than it did when it was coming towards you. So everyone kind of felt that? Okay, so that's an effect called the Doppler effect, and it has to do with how the wave propagates on its way to you. Okay, and if a wave is moving away from you, a wave source, then that wave hits you seemingly at a lower frequency than it was released by the wave source, so to speak. Okay, we say that wave has been redshifted. And the reason we say redshifted is because we're specifically thinking about light when we say redshifted. Red is the lowest frequency of light that we can see. Okay, so all light has a frequency. Red is the lowest. So something whose frequency has been downgraded by motion, something moving away from us, that wave appears to have a lower frequency than it actually did when it was released by the source. So we say that wave is redshifted. If something's moving towards you, when the ambulance comes towards you, the pitch of the sound sounds a bit higher than it should. We say that the wave has been blue shifted. The frequency is actually greater, okay, than what it is, than what the ambulance has released in its little siren. Okay, so if you hear an ambulance coming towards you, it should sound higher pitched than when it's sitting still. And if the ambulance is moving away from you, it should sound lower pitched. And I brought this little toy, and it kind of works. So it's going to create a sound, and you're supposed to kind of throw it or let it kind of move across the room. I didn't want to set up all the ropes, and then throwing it's kind of hard. But what I can do is I can actually just kind of goofily just kind of do this. And you should hear the sound actually change. Nothing's changing about the little toy, okay? What's changing is the frequency of sound that you're hearing. So it's kind of annoying. You hear the sound, okay? And tell me if you can hear a difference when I... Okay, do you hear that difference? Now, when I come towards you, you should actually hear the sound go a little higher, okay, in pitch. And when I go away from you, you should hear the sound kind of dip down in pitch, a lower kind of a sound. Okay, so... What?
Only when it moves.
Only when it moves, that's right. And for me, I was getting the exact opposite effect that you guys were getting, because when it was moving towards you, it was moving away from me, and so on and so forth. Okay? So we say that an object moving, a wave source moving away from you is redshifted, a wave source moving towards you is blue shifted. The blue and the red, again, are just because of the colors in the rainbow spectrum that we have. Okay, so the amount of redshift that we have, how much that frequency has dipped or raised, tells us how fast that object is moving. Okay? If I move this football 10 times faster, it would have distorted the sound 10 times more. All right, so what did Hubble do to decide the universe was expanding? The basic idea is he looked out there, he looked at stars, and he saw the light that came from them, and pretty much every galaxy that he could see was redshifted. Okay, so every galaxy that he could see, all right, was moving away from us. Okay, that's step number one. So almost none of the galaxies were blue shifted. Almost nothing was coming towards us. Almost everything was going away from us. Okay, and even more interestingly, the farther away something was at the time that he looked at it, the faster it was moving away. So something that was close to us was only moving away so fast. Something that was twice as far from us was moving away twice as fast. because the wave that came from that thing was twice as distorted by this moving Doppler effect. Okay, so this is one of the big evidences for the Big Bang, because in fact a universe which is expanding uniformly in all directions has this exact property. This little diagram here is supposed to be a piece of bread with raisins in it. And the idea is we take these two, which I can stop and read, but look at this first picture, okay? And you see that here we have two 5 centimeters and 10 centimeters. And as the expansion was uniform, they both moved twice as far away as they were before. So the 5 centimeter one moved to 10 centimeters, and the 10 centimeter one moved out to 20 centimeters. Which one moved farther from us? The one that was already farther from us. Okay? So the thing that's farther from us should be moving faster, because it's moving farther in a given amount of time. Okay? So that's actually the prediction of the expanding universe. And so the law, you should get a law, which Hubble discovered, that the farther something is away, the faster it should be moving away from us. So here's kind of his original plot. All right? This is the distance that an object is away, and this is the velocity at which it's moving away from us. And you see it forms a fairly nice straight line. Okay? And the actual shape of this line, the slope at which it moves, is actually a very important number in the study of the universe. Okay? So it tells us how fast the universe is expanding apart. All right? So this is not about dark energy yet, but it gets us set up for the ability to understand dark energy a little bit. So kind of the expanding universe is in its own right interesting, obviously. So let's talk about the expanding universe a little more. Normal matter, and now normal matter and dark matter. So even dark matter causes things to bind together. It's a gravitationally attracting thing. Okay? Normal matter and dark matter will both cause gravitational attraction. All right? The sun or dark matter, doesn't matter. It causes gravitational attraction. So what physicists thought prior to 1998, so this is getting much more recent now, is that certainly the universe, which is expanding and had been known to be expanding, should be slowing down in its expansion. Why? Because all the masses, as they're blowing apart, should be pulling on each other and kind of slowing that expansion down, kind of slowing the rate at which things are expanding. Okay? So there were two possibilities, two basic possibilities for the future of the universe. Possibility one, the amount of mass in the universe is quite high. The expansion goes but slows, it slows, and at some point it stops and then starts to reverse because the matter starts to pull in on itself, okay, and creates what we call a big crunch, which would be the end of the universe at the inverse of the Big Bang, basically a crunch instead of an explosion, so to speak. Okay, so that was one possibility. The other possibility is, okay, there wasn't quite enough mass, so the universe just expanded out and out, slowing. But by the time it slowed down enough, the mass was so far apart that they couldn't influence each other anymore, and the universe just kind of coasted out forever, which would be called the Big Chill, okay, because there'd be nothing left, basically. It would just be empty space everywhere. But it would still be slowing down in its expansion, technically forever. Okay. So those were the two possibilities for the kind of future of the universe and the way that we saw. So physicists tried, and it's a very difficult task, to try to figure out not only that the universe is expanding, but what's happening to that expansion. Is it slowing down a lot? Is it slowing down a little? That would tell us a lot about which one of these are the correct answer. Okay. What they found, the first scientists who were really able to measure this, they found something extraordinarily different than either of these two possibilities. They found out that the universe was actually accelerating in its expansion. So it wasn't slowing down at all. The expansion rate was speeding up more and more, faster and faster apart, not slowing down as anyone would have thought based on the properties of matter that tends to pull itself in. Okay, so the expansion of space is speeding up. We said the universe is not only expanding, but it's actually accelerating, getting faster and faster over time. Okay, so these three. Here's kind of a picture. We have this expansion, and now all of a sudden the universe appears to be expanding even faster than it ever was before. It seems to be spreading out at a greater rate than it has in the past, which means not only is it not slowing down, it's actually speeding up. So this was probably the most important discovery since Hubble in cosmology, because it says a lot about the universe. Very, very strange thing about the universe.
So
Yeah.
then, is there something on the other side pulling that to make it come faster?
So no, we don't think so.
Okay.
Although, can't really discount that. You mean outside of the universe, and so then it becomes very difficult to understand what does it mean to be outside of the universe. Okay, so these three guys won the Nobel Prize for it in 2011, so it's pretty recent. They discovered in 1998, they won the Nobel Prize in 2011 because no one's really sure. People said this is not very, it doesn't make sense, so let's corroborate it before you give you a Nobel Prize. But in the last 5-10 years, the evidence has become so strong that people have not really doubted anymore. So these guys finally got the Nobel Prize. Yeah.
Sorry to ask some questions.
No, that's good.
At the very first instant after the Big Bang, there was the inflationary epoch.
Yes.
Same thing, maybe?
Probably not. Yeah. The inflationary epoch was an exceptional rate of expansion, whereas what we see now is actually a minimal acceleration. So probably from different causes. Okay, so the universe is expanding and it's accelerating in its expansion. One of the most baffling things about the universe, actually, as we know it now. So what's causing it? Any ideas? Okay, so matter pulls in, doesn't push out. Okay, so some form of matter, no, matter pulls in. Even dark matter would not. Dark matter would actually be the opposite of this. Dark matter causes things to clump and collect and come together. Okay, dark matter is a form of matter. A form of radiation, maybe light is doing it. Well, it turns out when you analyze it, light actually is a form of energy which causes the universe to come together even better than normal matter does, even better than electrons and protons and neutrons does. So it's definitely not radiation. Okay, is it some strange form of energy that's like a repulsive type of energy that pushes things apart instead of pulling things together? Maybe. Okay, is it a property of space itself? Space itself just is a type of object or a type of thing which pushes itself apart, okay, due to some property fundamental, inherent to the universe itself. All right, so, no one seems to know. You realize dark matter is probably some type of WIMP. It's a particle. We don't really know what it is, but it makes sense. It's a normal type of thing. It's just a new type of thing. This is something unexplained, not known as to what is causing this. Okay, so Einstein himself would have been baffled, and kind of amusingly enough, Einstein, when he first published, so to speak, his theory of general relativity, he hypothesized that there was a property of space that caused a pushing apart. But he didn't do it for the reason that he observed the universe to be expanding apart. He did it for the reason that he was biased and he wanted the universe to be totally stationary. And to make that happen, he needed to put something there that would cause the universe to stay separate, to stay big and not collapse. But he had no reason for doing so. He just did it because he wanted it that way, which he realized later when the universe was shown to be expanding that he said it was his greatest error ever because he didn't do science, he did what he wanted. Okay, so, all right, but now this idea is somewhat making a comeback that maybe there is really a property of space that causes a repulsive-like effect. Okay, so what is it? Dark energy is in many ways much more mysterious than dark matter, much, much, much more. If you ask a physicist, dark matter is something that we might be on the verge of discovering and makes sense to us, even if we don't know what it is. It makes fundamental sense. Okay, dark energy is something that doesn't seem to make much fundamental sense. All right, so it's a type of substance which fills all space, or a property of space itself, whose effect on the universe is opposite to that of normal matter and dark matter. It causes the universe to accelerate in its expansion, almost as if it were a repulsive type of gravity, something repelling apart instead of pulling together. Okay, there are two basic possibilities. One is that dark energy is a property of space itself. It is anytime you have space, you have this energy which fills space, which is this type of repulsive energy. All right, and this is often called the cosmological constant. Cosmological because it fills all of space, and constant because it's always there. Okay. The kind of crazy thing about this idea is, as the universe is expanding, what's happening to the amount of space that exists? It's increasing. But the more space you have, the more of this energy you have that pushes space apart. Okay? So not only is the universe accelerating its expansion now, it's going to keep doing so, and it's going to get more and more and more. In fact, at some point, this dark energy is going to come to be the most dominant form of energy that there is. There's going to be nothing else besides basically dark energy. Okay. The other possibility is that dark energy is something that's not just a property of space, but something existing within space. It's kind of like a fluid, okay, but a fluid that we can't really detect or really understand at this moment. And this fluid fills space and has a repulsive effect on matter. Particle physicists do have ideas for what this fluid is. We have theories that say that such a fluid could exist. It's not mathematically inconsistent for such a repulsive type fluid to exist. We just have no hint that it actually does. All right, so there's no real good evidence for it. So there's all kinds of theories. Probably the most active area of research in fundamental physics is trying to figure out what this is. All right, that's in certain branches of physics, this is kind of the holy grail, so to speak. Yeah, Mike?
I guess there's evidence that it affects space because the dark energy is making it expand.
Mm-hmm.
Is there any evidence that it affects time at all?
Time, no, it wouldn't affect time.
Okay.
In the same way. It wouldn't affect time. It does affect space-time, but not in the way that you might think. In the most simple sense of like time will stretch out or something like that. That it won't be like that. Yeah.
Is there a possibility that there might be a violation of conservation of energy because of expansion of this space?
Yeah, so it depends on what you mean by conservation of energy, but dark energy definitely violates conservation of energy in a certain sense. In the sense that as space expands, it fills with more and more energy, which means the amount of energy in the universe grows more and more, which would seem to violate conservation of energy. There's a way to understand it in terms of the fact that this quantity does work on the universe, which increases the energy of the universe. That probably beyond our. Yeah.
Does this apply from a common reference point, or does it apply between individual bodies? And you're expanding from maybe a center.
Right.
Does it apply to other bodies that are separating other galaxies and
yes.
other?
So
everything's trying to get away from each other.
Yes. So there is no center. Okay. It's just everything's expanding away from everything else. There's no center of the expansion. It's all relative. Okay.
Relative to what though? Relative to each.
Relative to each other.
Each other, so everything is trying to get a. There's a force that's trying to repel each other. From
Yeah, in
each
some
other.
sense. The way I like to think about it is that between all objects, space is being created. So that would look to me like things are getting farther away. They're not getting farther away because something flicked them with their finger and they're going away. It's actually space between them is actually being created between them.
And the
So
more
they
space
appear
is created, the more that dark energy.
the more dark energy there's going to be.
Created?
Being created, yes. Yeah.
What does this have to do, if anything, with the Higgs field? Because Higgs field is an explanation for matter, right? And mass?
Yeah, Higgs field is an explanation for how the particles that we know, like electrons, protons, neutrons, how they have mass. Okay, obviously they do. So we want to know why, and the Higgs field is one explanation for that. This kind of directly doesn't have anything to do with the Higgs field, but indirectly it does in the following sense. The type of field that there is that creates a Higgs boson is a very specific type of field. And that field has never been seen before the Higgs boson. And it can be shown that that type of field, but that general type of field, but in a very different guise, so to speak, could be causing a repulsion of things. Could be this type of, this word, quintessence, that is this fluid that fills everything. It would not be the Higgs field, but it could be something in the general class of the Higgs field. And physicists would have had doubts about whether such a thing does actually exist at all. So if the Higgs field exists, then people say, well, we have one example of something like that existing. Maybe there are other examples that we just don't understand. So in that sense, but that's kind of indirect. But it's not a direct relation.
So would they define the Big Bang as the time when dark energy was introduced?
No, the Big Bang seems to be a time when another form of strange energy was introduced called, Danny said, had to do with something called inflation, which was another type of strange energy which seems to be necessary, but not related to dark energy as far as we know. The Big Bang expansion was seemingly a much more rapid expansion than we're undergoing now. And
but this is increasing though, right?
It is increasing. So at some point, someday, billions of years in the future, it will be an extraordinarily rapid expansion. Yeah.
So if I understood you correctly, the second hypothesis,
Yes.
that's really a field possibly?
It's a field, yes. It's a field that pervades space and time. It's a field that's out there.
Let me ask in relation to that, you're a particle physicist.
Yes.
Are there other kinds of physicists who would pose different questions to address these issues?
The only other, I mean, these are extremely broad. As you can see, there's some property of space, and there's something in space. So the only other explanation that people come up with is the law of gravity itself is wrong, so that when we think we're seeing things expanding apart, they're not, or accelerating in its expansion, it's not really. It's just that we're misinterpreting the data because the law of gravity itself is wrong. So that's the other possibility. That possibility is called MOND, which is called modified Newtonian dynamics. Somebody's saying that Newton's laws are wrong and it has to be modified. Newton's laws and general relativity have been tested extraordinarily well, kind of on solar system scales, but they hypothesize that maybe on larger scales in the solar system that Newton's laws and Einstein's law of relativity are wrong. So that's the other possibility. It's and I don't mean to sound like dismissive, but that tends to be dismissed among most physicists as having the least amount of kind of corroborating evidence, that idea. Yeah.
On those same lines, there's this deep assumption that always comes up, that the laws of physics here on Earth apply everywhere in the universe. Is there any way to test that fundamental assumption?
Yeah, so it's hard. There are a lot of lines of evidence along that kind of in that vein, right? You look at stars, for instance, and you compare them to our star, and we can detect a lot of things. Our star is pretty obvious as to what happens. We know a lot about it, our sun. You can look at other stars, and you can see the same things happening. Now, you could always concoct some extraordinarily complicated theory of the universe in which out there is different than here. But you'd have to tweak it so well to explain everything we see that most people don't like that idea, nor do they like the fact that the Earth is somehow special and different from everywhere else.
I've always heard the nature abhors a vacuum. You know, if there's a vacuum, something's got to fill it. So the more it creates a vacuum, the more it wants to fill it with probably this dark energy, the more vacuum. Does that make sense?
Yeah, it's a runaway process in a certain sense.
I have a question. In regards to dark matter,
yeah,
is it always associated with galaxies, and particularly the rim of galaxies, or are they ever like looking apart a space on Einstein ring, and then there's no galaxy there, there's no black hole there, or whatever's causing is too big for a black hole?
Right.
Are these clumps of dark matter that can exist outside of galaxies?
Just pure clumps of dark matter. Right. Probably not in that sense, but it's 85% of it anyway. So in other words, if you clump dark matter, you can start to clump regular matter too. In fact, one of the other lines of evidence for dark matter is the fact that there are galaxies at all. Okay? With just the amount of luminous matter we see, there wouldn't have been enough in the early universe to start clumping things together. They think dark matter was really the seed that started clumping things, and then other things started, like stars and things, started coming in, being clumped by the dark matter. Without dark matter, we would be way off in our understanding of the evolution of how galaxies form in the first place. It seems that dark matter is critical for the formation of galaxies.
So is it thought that we had dark energy before everything was created, or is it a result of the creation?
Well, dark energy would have, if it depends on the type of dark energy. If it's this first kind, then ever since the instant the universe was created, okay, ever since the instant of the Big Bang or the inflationary epoch or whatever you want to call it, there would have been dark energy. Now, the more space there is, the more dark energy there is. So at the very beginning, when space was quite small, it turns out dark energy would have been a not interesting thing. It would have been totally negligible because it was so little space. There would have been so little dark energy in that space. Okay? So as the universe evolves and regular matter becomes more and more dilute and the dark matter becomes more and more intense, so to speak, then the amount of dark matter in the universe gets more and more while the amount of regular matter gets less and less. And so the dark energy, I said dark matter, dark energy starts to kind of take over the universe. And so one of the questions is, where are we now? And this is quite interesting. Okay, here's data from the 2013, this is brandish new data, okay, from the Space Observatory that measures the cosmic microwave background, which tells us a lot about the universe. They give us a little pie chart, okay. It turns out if we consider matter and energy as kind of equivalent, which they are in Einstein's theory in a certain sense. If we take all the matter and energy in the universe and we break it up into how much there is, we see here's us, okay, ordinary matter, and it's not just us being like human beings with protons, electrons, neutrons, the Earth, planets, suns, stars, everything that we see, that we know about, that we seem to understand very well. 4.9% of the universe is made up of that. 26.8% of the universe is made up of this dark matter that we don't know what it is. We might have some idea of what it is. And 68.3% of the universe is actually dark energy. It's this type of energy that we don't understand at all. And that's the quite significant portion of the universe, is this type of stuff, whatever it is. Okay,
So as dark energy increases, what gives away in the pie chart?
These.
The dark matter?
Both the dark matter and the ordinary matter. Because what we're really interested in is the actual density of matter. So as the dark matter increases, as space increases, the matter, the regular matter, gets more and more diluted as it expands farther away, and these guys start to shrink. So someday in the future, this will all be dark energy, with the tiniest possible sliver that you can't see on the picture of dark matter and regular matter. And in the very far past, this was almost no dark energy, with almost all dark matter, ordinary matter, and it turns out also radiation like light, which actually takes up a 10 to the minus 4 on this chart. So the amount of energy in light is actually extraordinarily small now. Okay, so the future of the universe with this, here are the kind of pictures. So here's the picture of, there was no dark energy like we thought before 1998. The universe would expand, and then if it had enough mass, it would recollapse. Okay? Here was one weird possibility where the universe just actually goes out and sits there like on a ledge, but that's a weird, ignore that for a second. Here's the other possibility I mentioned, where the universe goes out, it slows down in its expansion, but just kind of coasts out forever. And here's the new paradigm, so to speak, since 1998. The universe actually will expand and then keep expanding, accelerating in its expansion, and eventually kind of just blow up, so to speak, in terms of the amount of space that there is in the universe. It will expand forever, more and more and more, okay, at a higher and higher and higher rate, forever, as far as we know.
We'll finally get inflationary rates.
Yeah, I mean, if you take this out all the way, it hits infinity at some point. So at infinite time, it becomes infinite acceleration of expansion. So, kind of this poem that people like to present, this Robert Frost poem. All physicists like to present this poem because it's this fire and ice poem. Okay, and so before 1998, it was actually unknown as to which end of the world would be, or end of the world's the wrong term, the future of the universe. And now it seems that we're here in the ice future, okay, where everything's going to go apart forever. And at some point, there's really going to be nothing left, because if things get spread apart by far enough, then at some point you can't see anything up there. It's all too far away to see.
Well, thank you, David.
Yes. little over.
I must say, there's nothing more satisfying than when a scientist ends a presentation with a poem.
Are there any questions, like, before, maybe we can go, of course,
But let me announce the next week talk.